Good morning and welcome to this lecture in our course on mechanical operations. In the last class we started talking about cohesion as a force that acts between particles in a suspension and which is the equivalent of the adhesion force between a particle and a surface. Again, cohesion is important because it determines how a suspension of particles behaves, particularly when you set it in motion. Under dynamic conditions, how particles behave, how they interact with each other, how they flow, how they stick to various surfaces depends very much on their cohesivity. And so it is important to understand cohesion forces, and we saw in the last class that there are some forces that are common to adhesion and cohesion, such as van der Waals forces, electrostatic forces and so on, but certain forces are different. And the reason that these new forces come into play is because as particles start to agglomerate, they go through various stages of cohesion. We saw that you initially start with this pendular state, then you go to a funicular state, then capillary state, and finally the droplet state. And in each state the extent of cohesion keeps increasing and different forces come into play. In particular, the three forces that are unique to cohesion are capillary forces, viscous forces and spring-like forces, right. Now very quickly you will see how these forces operate. So again, when you have two particles, you form a meniscus between them when they start adhering to each other, and there is an angle beta which is called the angle of cohesion, and this angle determines the extent of the surface tension forces and the pressure forces. Surface tension forces happen because of the formation of a meniscus between the two particles. The pressure forces happen because there is a pressure differential at the interface between the particles and the gas or fluid in which they are suspended. So the first force, which is the capillary force, has two components, which is F surface tension plus F pressure differential, and the surface tension force itself is given by 2 pi rp gamma times sine squared beta, and the pressure force is given by pi rp squared times delta p times sine squared beta. So this total force you can write as 2 pi rp gamma sine squared beta times 1 plus delta p over 2 gamma rp, and this dimensionless parameter is called the dimensionless mean curvature. And so you can basically write this expression as 2 pi rp gamma sine squared beta times 1 plus, this is designated as some h star, 1 plus h star. So if you look at this expression, I think some of the things that you need to bear in mind is that again you see a linear dependence on size. Rp, the capillary force scales as particle size. Now you might find that this is somewhat intuitively in conflict with what we have said earlier, that finer particles have a greater tendency to agglomerate. So we will come back to that point later on. In general, it is always true that if you have two very small particles versus two large particles, the actual magnitude of the force of adhesion or cohesion between them will be greater for the larger particles, if only because they have greater surface area of contact. That is a key differentiator. If you look at the adhesion force per unit area of contact, that will be much greater for a finer particle compared to a larger particle. But two larger particles being in contact always have the advantage that the area of contact between them is much larger, and the same thing applies to adhesion also. Even though we do say that finer particles have a greater tendency of adhesion to a surface in terms of actual magnitude. A larger particle will always have a greater magnitude of adhesion. So, why do we say that larger particles are easier to remove than finer particles, or why do we say that larger particles tend to cohere less than finer particles? Can anybody offer a logical explanation for that? I mean, do you agree that if you look at particle adhesion to surfaces, let us say that you see a powder and there are some fine particles and some large particles, and you just blow on it, which particles are going to get dislodged first? The larger particles, right? So, they are clearly less strongly bonded to the surface, but we just said that a larger particle should have greater force because there is more contact area. So, do you see a conflict there, or do you have an explanation for it? Actually, if you had listened to my NPTEL core lectures, you would know. So, it's, but the reason is that even though the adhesion force or even the cohesion force scales as particle size, any force that tries to remove the particle from the surface scales as particle size squared. So, as the particle gets larger, even though its adhesion force may be increasing, the force of removal increases as the square of the size. So, if you take the ratio of adhesion force to removal force and call it like a net adhesion force or effective adhesion force, that will scale as 1 over particle size. For example, let us say that you have a dust particle on your palm and you blow it off. What is the removal force? It is aerodynamic shear, right, and that goes as velocity squared or sorry particle size squared, because it goes as the area of the particle. So, that is the key point, that most common particle removal forces, whether it affects adhesion on surfaces or particle adhesion to each other, will scale as particle size squared, whereas the adhesion forces or cohesion forces will scale as particle size, and that is why it is easier to break apart agglomerates of larger particles, and it is easier to blow off particles sitting on surfaces. Okay. All right. The second type of force are the viscous forces, and the viscous forces can be split into normal and tangential forces, and the normal force is given by 6 pi rp times mu times a factor mu by s, which is the distance of separation between the two particles. Sorry, there is also a velocity term Vn, whereas the tangential force is given by 6 pi rp mu v tangential times 1 plus 0.5 logarithm of again rp by s. Again, you see the dependence is predominantly, sorry, this should be rp by s, linear with respect to particle radius. Now, a couple of things, there are lots of forces that affect cohesion, but the one common element you will see, there are two common elements. There is usually a linear dependence on size in terms of the total force, and secondly, virtually all these particles are attractive in nature. In terms of cohesion, the only force that can be potentially repulsive in nature is charge based. If two adjacent particles happen to have the same charge, they will repel each other. But if you take that out of the equation, virtually every other force that applies in cohesion is attractive in nature, and that is why there is an inherent tendency for suspended particles to try and get together and form agglomerates rather than remain suspended discretely as particles in solution. The third type of force is the spring-like force, and this refers to the fact that when you have two particles that are suspended, they almost behave like they are connected by a spring, and as one of the particles drifts away with a relative tangential velocity, there is also a tendency to bring the particle back to its original location. So, it behaves like a spring both in the normal direction and in the tangential direction. you can almost visualize two particles that are suspended in a fluid as being connected by a virtual spring. So, anytime they try to drift apart either in the normal direction or in the tangential direction, immediately they want to jerk back together, okay, and that again leads to higher cohesion forces and so on. So, here the force, the normal force is given by a factor Kn times alpha to the power 3 by 2, where alpha, if this is dp1 particle diameter 1, particle diameter 2, and this distance of separation is some s, it is dp1 plus dp2 minus s, and this Kn parameter is given by 4 by 3 times a dp star times square root of E star, where again the 1 over dp star equals 1 over dp1 plus 1 over dp2, and E star, 1 over E star is given by 1 over 1 minus nu 1 squared by E1 plus 1 minus nu 2 squared by E2, where E1 and E2 are Young's moduli and nu is the Poisson's ratio. So, these are both effective diameter and effective Young's modulus. So, the spring like force in the normal direction simply goes as effectively particle size to the power 1.5 roughly. In the tangential direction, there is an initial force at time equal to 0, which is a tangential spring force, and that is then reduced by a factor minus kT delta s, where kT is a constant and delta s is the displacement. So, delta s is delta t times Vt, where Vt is the effective or the differential tangential velocity between the two particles, and delta t is the time increment. So, for every time increment delta t, the one particle will drift away from the other particle at distance delta s, and then the spring like force will try to again draw them back together. Of course, eventually as delta s increases beyond a certain value, the particles do not know that each other exists. So, the force will drop off to 0. So, the tangential force is only effective as long as the particles are reasonably close together, which means that this tangential force becomes increasingly important in concentrated solutions, because as the concentration increases, the distance of separation between any two particles decreases. So, the tendency for the tangential spring like force to keep the particles together increases. Alright, so the point is there are many different cohesive forces: van der Waals, electrostatic, capillary forces, viscous forces, spring like forces, even the hydrophobic, hydrophilic forces that we described earlier. As we saw, these are very important in deciding whether two particles in suspension want to adhere to each other or repel each other. Two hydrophobic particles in a hydrophilic medium will tend to attract and so on. So, the hydrophobic slash hydrophilic forces are also important, and of course, if they are magnetic particles, then magnetic forces will become important and so on. But the point, so in general all these forces are there, and as I said earlier, many of them are attractive in nature. So, what happens is, if you start with a suspension of particles and you track and you want to track how cohesion is happening over time, what would you measure? I mean, what would be the simplest parameters for you to measure? Any idea? You have a suspension of particles and you want to know if cohesion is happening, and if so, how rapidly. What would you measure? There are two parameters that can give you some very good indications. The first is number of particles. If cohesion is happening, the number of particles will decrease, right? The second related parameter then would be mean size. If cohesion happens, the mean size will keep increasing. So, in order to assess the stability of a particle suspension in any processing industry, the two parameters that people track very closely are the count of particles and the mean size of particles. So, if you plot versus time the number of particles larger than a certain size, let us say we can plot all particles larger than 1 nanometer for example. How will this curve look? In where there is extensive cohesion, you will see a behavior that looks kind of like this. If there is no cohesion, what will it look like? Straight line, right? So, the number of particles will just remain. Can you imagine a situation where this number will keep increasing with time? What would cause that to happen? When would you expect to see a behavior that looks like this? Dissolution. If the particles are soluble in the medium that they are in, larger particles will keep breaking up into finer particles, right? So this is a case where there is no cohesion, and this is a case where there is only no cohesion, but actually there is breakup of particles happening due to various reasons. Okay, and then if you plot mean size versus time, you should see the reverse trend, right? Initially you should start with a low value and go to a high value, and this is under highly cohesive conditions, and under no cohesive conditions this is the kind of behavior. The particle size will also remain constant. Particularly when you have particles in suspension and you see that the mean size is increasing, that is clearly indicative of cohesion happening. But again, what happens? What do you see the reverse trend? What would that tell you? Again, it could be dissolution and other breakup mechanisms, or it could be also simple sedimentation. It could be that larger particles are just settling down and going out of your measurement range, because we are talking about measuring counts and particles in the suspension, which means that the particles have to stay suspended in order to be measured. But if your particles are too large, they will just settle and you may never count them. So, when sedimentation happens, you can actually see this type of behavior also. So, very qualitatively, this is how you would check for cohesion happening in a suspension. Well, qualitatively, I mean it is certainly quantitative, but what I mean is that this is a very simplistic picture of what is happening. In reality, cohesion is not a monotonic process. There will be incidents where two particles will aggregate, but then they may break apart again, right. So, because it is not an irreversible process unless it is chemical bonding, but as long as the cohesive mechanisms are physical in nature, they can always be reversed, and two particles that have come together can be broken apart, right. And so, there is something called population balance modeling that tries to do this very rigorously. It takes into account all generation processes and all consumption processes in every size range and tries to predict the behavior of a particle population as a function of time over an entire range of particle sizes. So, all these different mechanisms are taken into account, and the reversibility versus irreversibility of the mechanism is also taken into account. But this is a fairly simplistic representation which in most cases will turn out to be reasonably accurate. So, if you try to express this mathematically, there is an expression which is based upon a lot of empirical data gathering that says 1 by n over t, which is the number of particles at any time t, is related to the number of particles at time 0 by an expression that looks like this: 4 by 3 pi k t c c t over mu, where k is the Boltzmann's constant, capital T is temperature, Cc is the Stokes Cunningham correction factor. Are you familiar with the Stokes Cunningham correction? It is also, Cc is called the Stokes Cunningham correction factor, and in fact the full name is Stokes Cunningham slip correction factor. What it tries to correct for is the fact that with virtually all of our mathematical models we are assuming continuum behavior. What is continuum? A continuum basically implies that there is good coupling between adjacent layers of molecules. So that you can take a system and you can assume that every layer of molecules is coupled to the next layer of molecules. So it all behaves as an integral whole, as opposed to what is the other limit? It is free molecular range. In the free molecular regime, every molecule is free to behave as it wants. So typically the distance of separation between adjacent molecules is very large, and these molecules are just flying around, like they didn't even know that the adjacent molecule existed. Whether you are in the continuum regime or the free molecular regime depends on a number called the Knudsen number. The Knudsen number measures the ratio of particle size to the prevailing mean free path. If the particle size is smaller than the prevailing mean free path, and the mean free path, by the way, is the distance that a molecule can travel before it encounters the next molecule, or a particle can travel before it encounters the next particle. So the Knudsen number measures this ratio of dp over lambda, where lambda is the mean free path and dp is the particle size, and if the Knudsen number is much smaller than 1, in other words the particle size is much smaller than the typical distance of separation between two adjacent molecules, that is called the free molecular regime. Whereas if this is greater than 1, it is called the continuum regime, and actually if it is equal to 1, that is called the transition regime, and that is actually the most difficult to deal with mathematically. But anyway, in most systems that we deal with, including what you will encounter in mechanical operations, you typically make the continuum approximation. Okay, you assume that the prevailing mean free path is smaller than the prevailing particle size. But as you can imagine, as particles get finer and start approaching nano dimensions and so on, this assumption can break down. And also, even though this assumption may be accurate for the system as a whole, there may be isolated locations in your system where the assumption breaks down. Then what happens is something called slip. Slip happens when the continuum assumption breaks down, and at local neighborhoods molecules start to behave, or particles start to behave like they are in the free molecular regime. So you have to make an appropriate correction for this, and it turns out that very approximately this parameter Cc is proportional to 1 over dp. So as the particle size gets smaller, Cc quickly becomes much larger. So in this expression, if you are just looking at parametric dependencies, you can remove the C and substitute with a dp in the numerator. Of course, this constant will then be changed from 4/3 to a different value. So now this is a very important expression in the study of cohesion dynamics, because it gives you a lot of clues about how cohesion dynamics are affected by the various process parameters, and also how you can try and control them. For example, if you take 1 over n by t minus 1 by n at t equal to 0, the expression on the right hand side is basically, you can call it your extent of cohesion, because it represents the difference in the number of particles from at time 0 to the number of particles at time t. So if you look at this expression as a representation of cohesion strength, then clearly temperature plays a big role. As temperature increases, cohesion increases. Why is that? Because as temperature increases, particles just like molecules become more energized, they are likely to move around more, and the more they move around, the more they are likely they are to find adjacent particles and stick to them. So, temperature rise has an immediate consequence on cohesivity. In general, as temperature increases, cohesion increases. Time is also in the numerator. Again, this is a trend we always see, that with the progression of time, cohesion increases, and that is again because as time passes by, the particles have more time to find each other and stick to each other. So, cohesion will increase as temperature increases and as time increases, and cohesion will increase as the particle diameter decreases. And again, the reason for that we will see more when we talk about particle transport phenomena, but as particle size decreases, the diffusivity increases very rapidly, and so a very fine particle will diffuse much faster than a larger particle, which again makes it more likely that it will find its nearest neighbor and stick to it. So, anything that promotes the mobility of particles promotes cohesion. Okay? That is one simple way to look at it. Mu is the viscosity. The less viscous a fluid is, the more likely that cohesion will happen. Again, once you have thought about this in terms of mobility, that makes sense. If you have a less viscous fluid, there is less resistance to particles moving around. So, they are likely to move around more, find their nearest neighbor and attach themselves. So, now if you want to design a system which minimizes cohesion, then what would you do? Obviously, there are hints here. Temperature at which you keep your system, thus less likely that cohesion is going to happen. Actually, you can imagine an extreme case. Suppose you have particles in a suspension and you want to make sure that they never agglomerate. How would you do it? Freeze the thing, right? Because once you freeze it, particles are stuck in one place. So, but basically as you reduce the temperature, you kind of start defeating cohesion. Time you cannot do much about, but one way you can control time is, if you are going to prepare a suspension, do it just before you are ready to use the suspension. Do not prepare the suspension and keep it for a week and then try to use it, because the size distribution and the count distribution will be completely different from the time you prepared the suspension. So, just in time preparation of particle suspensions enables us to defeat time as a parameter in promoting cohesion. Particle size, you may or may not be able to play around much, but in general realize that as particles become smaller, it is going to be more of a challenge to keep them apart. So, you have to do more playing around with the other parameters, and of course, viscosity. Increasing viscosity is a good thing, and there are certainly viscosity enhancers that you can use, or you can use solvents that are more viscous to keep particles in suspension longer. So, there is a lot of clues that you can get from this expression regarding how you can keep particles from cohering. But in general, cohesion is going to happen, and initially the cohesion will be pairwise, and then they will start adding more and more particles to the matrix, and you will start getting these clumps of particles, which is, as I said, not to be desired in most cases. However, there are certain industries, there are certain applications where you do want good cohesion. An example is the pharma industry. You know, in pharma applications, you are trying to formulate these tablets, right? We all have taken tablets for various reasons, and the tablets are clearly consisting of many particles that are agglomerated together. Now, when you buy a tablet, what do you want? You know, when you first purchase it, you want it to be firm. You don't want it to be in a state where it's semi molten or liquid, right? You want it to be a solid tablet. But as soon as you swallow it, you want it to dissolve immediately and release all the active chemicals. So, whatever you are taking the tablet for can be fixed or cured as quickly as possible. So, it is almost like, again, two conflicting requirements. You want a tablet that is very coherent to begin with, but at the same time you want it to be such that it will dissolve very quickly either in water or in your saliva or whatever you want. So, there are some interesting requirements in the pharma industry that in terms of how do you deal with cohesion and adhesion and so on. See, adhesion is something you want to avoid again, because if you have a bottle and you are buying tablets, you do not want the tablets to stick to each other, right. So, you want to prevent adhesion, but you want cohesion. So, there are a lot of interesting science, that is where the particle scientists make their money. How do you design these medical supplies that satisfy all these different requirements that people have. So, when you talk about cohesion, not in a liquid suspension state, but rather in the case of a solid product where you do want some amount of cohesion, you actually want to try and promote cohesion in that case. So, how do we do that? So, the guiding principle is that if you look at the cohesive strength, let us just call it some C. Let us say this is a cohesive strength of a tablet. Tablet consists of many fine particles that are adhered together. It turns out that this is basically a sum of the cohesive strengths of the individual particles that make up the solid powder material. So, that again has some interesting implications, which means that if you can formulate your tablet with more particles, you can actually increase its strength, maybe. Now, what is a simple expression for the cohesive strength of just pairwise particles? You can just write it as some 3 pi r gamma, where this r is a weighted radius of the two adjacent particles, and gamma you can simply write as gamma 1 plus gamma 2 by 2, where these are surface energies. So, here again in this expression you will see that the cohesion force scales as size. But let us talk about something called cohesivity. Cohesivity, let us call that some alpha, is the cohesion force per unit effective interfacial area. Okay, cohesion force is a total force, but cohesivity, it is like the difference between resistance and resistivity, right. Cohesivity is the cohesion force divided by the effective interfacial area between two particles. Very approximately then this alpha can be written as 3 pi r gamma divided by some pi r squared or 4 pi r squared, and clearly this again goes as 1 over r. So, cohesivity goes as 1 over size. The cohesion force itself goes as size. So, if you are trying to maximize cohesion, what do? You maximize the interfacial area. And how do you do that? By making the particles extremely smooth, so that the contact area is maximized. As we discussed earlier, roughness has an influence on not only particle to surface adhesion, but also particle to particle adhesion. So, if you can make two perfectly smooth spherical particles and you bring them in contact, in principle the cohesion force between them is infinity. Well, it is infinity more for two flat plates that you bring together, but for two spherical particles that you bring together also, the cohesion force can be very high. But if you do have two rough particles that are next to each other with some distinct roughness elements, how is that going to change your cohesion force? What it really changes is this value r. This value r now, instead of paying the diameter or the radius of the particle, will have some value, let us call it a0, which is an effective radius of contact, and correspondingly this 4 pi r squared can be replaced by an effective area of contact, let us call that capital A subscript 0, which depends on the roughness characteristics of the particles. Okay, so this alpha value for a smooth particle may have a certain value, but for a rough particle it may have a completely different value depending on the ratio of this r to A0. In general, you would expect that the A0 value would be smaller than r, because now you have discrete points of contact rather than a continuous surface of contact, and similarly you would expect that this capital A0 would be smaller than the 4 pi r squared, but that is also going to affect this value r, right. So, the reduced radius of contact is going to have an influence on both the numerator as well as the denominator in this expression. So, going back, we can write this F cohesive as some alpha times A0, where alpha is your cohesivity and A0 is the effective interfacial area of contact. For again for two spheres, smooth spheres, this may simply be the radius of the particle, but for two rough surfaces, rough particles that are in contact, it is going to depend on the roughness distribution, and in fact it is going to be a function. So, this is going to depend on the roughness asperity Ra. It is going to depend on, well, it is going to depend on two things, right. It is going to, if this is your roughness, it is going to depend on this height, and it is also going to depend on the distance between two successive roughness asperities. So, if you call this Ra, which is the height of these asperities, and if you call this some lambda A, which is the distance between two asperities, they both have a significant influence on the cohesive tendencies of these particles. And of course, other parameters like elasticity, Poisson's ratio are also important, because just like adhesion, cohesion also depends upon how the two particles react. Is there any give, as two particles approach each other, are they going to present very hard surfaces to each other, or are they going to try and accommodate each other? The more accommodating the particles are, the greater will be the cohesive force that develops. So, clearly those parameters are also involved in this expression. So, when we look at the effect of cohesion in a practical manufacturing environment, one of its key effects is how it determines the integrity of the product that you are making. The other key effect of cohesion is in the flowability of the suspension. In many practical factory type of applications, you would want to take a slurry of particles and make it flow in certain directions. It may be simply gravity assisted discharge, or it may be a pressurized conveyor system, but whatever it is, you want this population of particles to be transported from point A to point B, and how they get transported depends also very much on their cohesive properties as well as their adhesive properties to surfaces. So, in the next class we will discuss flowability of materials and the effect that cohesivity and adhesivity have, and how these can be modeled. Any questions? Okay, I will see you tomorrow.